Welcome to the exercises for chapter 6. This chapter is all about data transformations. This is when you apply some algorithm or some mathematical formula to transform the values of your data from their original scale or distribution to a different scale or a different distribution. Let's begin with exercise 1. This exercise is all about min-max scaling. And we're going to start by combining equations 6.9 and 6.10 into one equation that we can use to transform a data set from any min-max boundaries or values to any other min-max values. So there's more to do here, but first let me scroll up and show you these two equations. Here we have equation 6.9. The purpose of this equation or this transformation is to get a data set from any range of numerical values to a range of numerical values starting from 0 and going up to 1. So regardless of the scale or the boundaries of the original data set x, if you apply this formula, so each new value of x, which here I call x tilde sub I, so each index value, each data point x tilde I, is equal to the original data point minus the minimum of the total data set divided by the range of the data, so the difference between the largest value and the smallest value. Now, after you apply this formula, all of your data are guaranteed to be in a range of 0 to 1. This transformation does not change the shape of the distribution of the data. So if your data are clustered in a particular way, if they're Gaussian distributed or log normal distributed, any kind of distribution, the distribution shape remains identical. If there are outliers, they are unchanged. The only thing that's changed is the numerical scale of the data, and here they range from 0 to 1. Okay, so then that's equation 6.9. Then we have equation 6.10, and here this will transform a data set from a range of 0 to 1 to a range from A to B. So after you apply this formula, you will get any numerical range that you want. So any lower boundary A and any upper boundary B. Okay, so the goal of the first part of exercise 1 is to combine these two equations, 6.9 and 6.10, into a single equation. Here they're two separate equations. We want one equation. It's actually not that difficult because you can see that x tilde is isolated over here. So really all you have to do is plug in all of this business over here, this fraction of x tilde in place of this. Otherwise, pretty straightforward, but good exercise. Once you have that formula written down on a piece of paper, you want to translate that equation, that transformation, into a Python function that takes any numerical data set and returns a min-max scaled version of that data set using boundaries that you get to specify. And you want this to be in a Python function because there's another exercise later on. I think it might be exercise 3. But there's another exercise where you are going to use this function. So let's see. So your function can take 3 inputs, the data set, the lower boundary, and the upper boundary. And then you can test it using 10 normally distributed numbers and rescale them to a range of 14.3 to 34.0. 2 arbitrary numbers, but just to, check to make sure that your code is correct. Okay, so that was part 2 of this exercise. Part 1 was this paper and pencil work. Part 2 is getting this function. And part 3 is to find a Python function that applies the same min-max transformation that you are applying here in your handwritten function. Now, I'm not going to tell you the name of the function or how to use it. That's up to you. I've mentioned before in earlier videos and earlier chapters that knowing what you want to do and having to do a little bit of Google searching or Bing searching or whatever to find that function and figure out how to use it, that is an important real-world skill that you need to know to work in Python. So anyway, the point is find a Python function that reproduces these results without you having to code this mathematical transformation yourself. All right, so I hope you enjoy working through this exercise. Now I will switch to Python and show you my solution. Let me start by showing this comment down here. So this is the code all in one line. This is the formula in one line of code that implements exactly this min-max scaling to any arbitrary set of boundaries. So x minus the min divided by the max minus the min times the new max minus the new min plus the new min. So it's just basically a lot of like shifting and scaling and so on. Nothing super difficult, but it does take a good minute or two of your life to work through the math. Okay, so here I have the function that does the scaling. You can see it takes a data set as input, the desired output minimum, the desired output maximum, and then, yeah, here is, let's see, so here is the scaling to 0 to 1, and then I scale to the new arbitrary range, and then I just return that. Yeah, and you can do all of this. You can implement this whole function in one line. I mentioned in, I think it was in the previous chapter in one of the exercises, that certainly when you're getting started, I definitely recommend writing out in multiple lines of code whatever is the operation you need to implement. And then once you're comfortable that this works and you understand it, if you want, it's really not necessary, but if you want, you can compress it into a smaller number of lines of code. Anyway, here I will test it on some data. So I have normally distributed numbers, and then I want to have them be scaled between 14.3 and 34. So here is my function, and here is the empirical minimum and maximum, which exactly matches the desired output. Okay, so here's how you do it in Python using sklearn, scikit-learn. Scikit-learn.preprocessing, there's a module called min-max scaler. Or sorry, it's a class. This is the module. And then, so you have to define a new instance of this class with this feature range. And then you have to make sure the data are reshaped because this thing is really finicky. You have to fit the data or fit the scalar and then apply the scalar to the data. I don't know. To be honest, okay, let me talk about this in a moment. Okay, so here we get pretty accurate results. You can see there's like some ludicrously tiny rounding error over here, which doesn't really matter. Here, I'm confirming that the result of my function and the sklearn function is the same. So here I'm just printing out all the data values next to each other. And here is a scatter plot, which provides some geometric intuition that we are getting the same results. Now, this is an interesting discussion of when you should use built-in functions that are supplied by professional developed toolboxes like scikit-learn versus when you should write your own functions like what I just did earlier. To some extent, it's up to you. There are arguments for doing both ways. This is a case where I just find this to be totally insane. I mean, this is such an easy transformation to apply. And then to have to go through all these lines and deal with classes and instances and reshaping to get a multidimensional array, I find this to be insanely complicated, pointlessly, gratuitously complicated for such a simple operation. I would never actually use the scikit-learn.preprocessing library just to do this min-max scaling. I would just do it on my own. If you want to use scikit-learn, that's great. But I think it's really handy to understand the math and see how easy it is to implement the math yourself with really just one line of code. Anyway, I hope you found this exercise to be interesting and enlightening. Here we are in exercise 2 of chapter 6. The goal of this exercise is to explore different transformations, in particular the natural log transformation and the square root transformation, to different distributions in hopes of making those distributions more normal, so closer to a normal distribution. Now, the logarithm, natural log transformation, and square root transformation often work roughly similarly. They often produce kind of similar results. So sometimes it doesn't really matter which one you use. They both work reasonably well. Sometimes it does matter. For example, if you have zeros in your data, then you can apply the square root transformation, but you cannot apply the log transformation, at least without first shifting the data and that's because you cannot take the log of 0. Now, I want to go back to figure 6.9. Figure 6.9 shows some data, and here is the histogram of the raw data, and then I applied these two transformations, the natural log and the square root. Now, neither of these transformations are perfectly normal, but that's actually fine. Very often in statistics and in machine learning, data science more generally, it's okay if the data are not exactly perfectly, purely, normally distributed, but it is important to make them closer to a normal distribution or approximately normal-ish distributed. This is clearly not a normal distribution. Here we have the natural log and the square root. Now, again, neither of these is a pure normal distribution, but the natural log is certainly a lot more normal-ish. This looks more like a normal distribution with just a large negative tail. Square root distribution here looks nothing like a normal distribution. So the question is that always the case? Is the natural log always better than square root? Well, you can already imagine the answer is going to be no, it is better in this particular case for getting the data to approach a more normal distribution. But the goal of this exercise is to explore this in more detail. So in particular, we are going to recreate that figure, but use, instead of using x squared, which is how I define those data for x coming from a normal distribution, use x plus 3 squared. So not x plus 3 squared, that would be x plus 9, but the quantity x plus 3, and then you square that quantity. So effectively, we are applying two transformations to these data. First is a linear transformation where we are just shifting all the data by 3, and then a square transformation, so a nonlinear transformation. And now the question is, which of these two transformations, natural log or square root, will get these data closer to a normal distribution? And what I want you to do is then create some QQ plots, which you see here. So QQ plot of x squared, QQ plot of the square root of x squared, and here we have x plus 3 squared and the square root of x plus 3 squared. And it's pretty obvious that this looks really great. This looks really close to a normal distribution. And then, you can also repeat this plot for the log transform of x versus x plus 3. Okay, so lots of interesting things to explore, but a very simple take-home message. And that take-home message, which I hope you'll be convinced of by the end of this video, the take-home message is you should try different kinds of transformations. There's no single transformation that is guaranteed to be the best for all kinds of data characteristics. Okay, so there's a lot of code here for exercise 2, but actually it's pretty much straight up just copy pasted from the code that creates the figure 6.9, which is presented earlier in this code file. So as I write in the text, if you want an extra challenge, you can write code from scratch to create that figure. Otherwise, you can also feel free just to copy and paste that code and modify as you need. In fact, the only thing that I've modified from earlier in the chapter is this line here. So here I create normally distributed random numbers. Originally it was Gaussian distributed numbers squared, but now here I'm just adding 3 before squaring. So we're just shifting the data. In fact, you could also use the normal function here to get normally distributed data with a population mean of 3. Okay, so then I take the histogram of the data, histogram of the log transform of the data, and the histogram of the square root transform of the data. And that you see here. And now we can see, so here's the data histogram, the raw data. And now when we look at these two distributions, the log still looks reasonable. I think this distribution is slightly more normal looking than this, but it's pretty clear that the square root transformation is way better. I mean, this really looks like a shifted normal distribution. So that looks great. Okay, so now we have these two data sets, x squared and x plus 3, quantity squared. And now we're going to make a bunch of QQ plots of these different data, and then with and without the transform here. Okay, and then this is let me shrink this a little bit. This is the figure that I showed in the book text. And basically the idea is that the square root transform works kind of well. You can see this is certainly closer. It's more normally distributed than this is, so helps a little bit. But this is really beautiful. This looks like an amazing normal distribution here. Okay, and now what I want to do is go back and apply the log transform. So exactly the same code, exactly the same data characteristics, same same QQ plots, everything is the same. I'm just replacing the square root with the log. Now, I'm not updating the titles, so the titles are all incorrect. So don't pay attention to this here because this is actually the log of x squared, not the square root. But what I want to show you is that, remember, this was the plot where with the actual square root transformation, this looked so perfectly normal. This looked amazingly like a normal distribution with square root. And now with the natural log, this does not look like a normal distribution at all. Again, the main take-home message from this exercise is that there are many different transformations that you can apply to your data. It's very difficult to say that, transformation X is always the right one to use in situation Y. You have to gain some experience, you have to play around, you have to explore and experiment with different transformations to make sure that the transformation you are applying to your data is appropriate. Welcome to the video for exercise 3 of chapter 6. This exercise is not so difficult. I don't think you will find this to be too challenging, but it is important. The concept, the theme, the message, the upshot, what other words can I use? The take-home message from this exercise is pretty important. So here I say that some data transformations are lossy, meaning that you transform the data and you lose information. And other transformations are perfect. They are not lossy, meaning you can transform back and forth all day long, and you will never lose any information. So how about Z normalization? Is that a lossy transform? To find out, I want you to try and solve equation 6.1 for xi. And if that's possible, then the transformation can be inverted. Okay, so let me scroll up to equation 6.1 so we can all see what we're referring to here. Here is equation 6.1. So we have our new transformed data value, z sub I, and the I is for the ith data index, the ith data value, is xi, so this is the original data, minus the data mean divided by the data standard deviation. Okay, now if this were a lossless data transformation, then it would be possible to solve this equation for x sub I. If that's not possible, then we have a lossy transformation. Okay, well, the answer is yes, you can. This is a lossless transformation. It is possible to solve this equation for x sub I. It's not too difficult. Please take out a piece of paper and a pen or pencil or draw in the sand or, whatever you like to do. And solve this equation, rewrite this equation for x sub I. It'll take you a minute or half a minute or so. And you can do that. That proves that this transformation is invertible. Okay, so once you have the formula worked out, translate your inverse transformation into code, and then test it by creating a dataset of 25 randomly selected integers between 4 and 14, so this would be inclusive, 4 and 14, Z transform the data, and then back transform the Z transform data. So you want to go from these integers to a Z transform data, and then take the, basically undo or invert the Z transformation, back transform, and then make sure that the original data, so these data you generated, and the Z transform and then inverse transform data are identical. They should match identically. Okay, so that is your task. And now I will switch to Python and show you my code solution. I'm not going to walk through all the steps of transforming that Z transformation formula because, I don't know, I think it's relatively elementary algebra. But you should end up at something like this. So x equals zs plus m, where z is the Z transform data, the standardized data. S is the original standard deviation. Obviously, this is not the standard deviation of the Z transform data that is trivially equal to 1. And M is the mean of the original data. Again, that's not the mean of the Z transform data that is trivially equal to 0. So this back transformation or inverse transformation is possible only if you store the mean and the standard deviation of the original data set before it gets transposed. Okay, or transformed, sorry, not transposed. Okay, so now we will empirically demonstrate this. So here I generate 25 random integers. Here I take the original mean and the original standard deviation, transform the data to z-score, and then back transform the data. Okay, so now data in and data should be identical. And, we're dividing, we're doing some mathy stuff here. So it is possible that there will be some really, really tiny differences between data in and data just because of precision errors and so on, but they should be more or less identical. Okay, so there's a bunch of ways you can do this. You can print out both vectors and inspect them. You can subtract them to see that their difference is 0. You can plot them on top of each other to see that they overlap. So multiple ways that you can see that they are the same. So here in this plot, you see that they certainly look like they are the same. And I am going to, let's see, so this is data minus data in. So I'm also going to say data minus data in. And here we see that all of the differences are exactly 0. So that confirms that this is a lossless transformation. I like to have varied levels of difficulty in the exercises that I create for this book and for my other books and courses and so on. So that means that some exercises are pretty simple, don't take too much time. Some exercises are kind of medium level of difficulty where I try to make it a bit challenging but not too hard. And some exercises are more involved and require some creative thinking, some problem solving, a little bit of luck and guessing, and just some slugging away. This exercise 4 of chapter 6, I think is a little bit challenging. Once you have an idea of how to solve it, the code is not so difficult, but coming up with the solution, I think requires a little bit of thinking, a little bit of integrating across different concepts in this chapter and in earlier chapters. And anyway, let me describe the exercise. So what I want you to do is start with 313 numbers that are randomly drawn from a uniform distribution between 3 pi and e to the pi. No reason, I just happen to like how these two numbers look. Okay, so you start with uniform distributed numbers in this range, and your mission, should you choose to accept it, is to transform this distribution into a normal distribution that has the same mean. So it should go from a uniform distribution to a normal distribution, but with the constraint that the average of the distribution needs to be the same before and after the distribution, the transformation, I mean. And then make some histograms like this. Here you see the original data in black. So uniform distribution, of course, is not a perfect uniform flat distribution just because of sampling variability and noise and so on. And here is the transform data, and here is the average. So the averages are the same, and the distribution shapes are significantly altered. Okay, so that is your mission, and now I'm going to switch to Python, explain how I solved this project, and then show you my solution. So the way that I solved this problem, this exercise, is by leveraging the fact that the Fisher Z transform can transform a uniform distribution into a normal distribution, or at least a distribution that approaches Gaussian or normal distribution. But the Fisher Z transform only works for data that are between -1 and +1, and those are exclusive bounds. So excluding exact -1 and excluding exact +1. So therefore, what I decided to do was apply the min-max scalar that I wrote for exercise 1 to transform the data from their original bounds into, and that you see here, so here's the data uniform distributed, into a new data set that has that goes from minus 0.999 to plus 0.999. So basically -1 to +1, but excluding those exact boundaries. Okay, so now now we're not finished, right? This is normally distributed data, but the average of these data is going to be 0 or somewhere close to 0. So then let's see, actually it's here. Okay, so scale the data to -1 to +1 and then apply the Fisher-Z transform. Now here is where the data are roughly normally distributed, but here they have a mean of 0. So then we need to shift the data basically to add on the mean. And I do this here by first shifting the data so it's guaranteed to be mean-centered, and then shifting it back up to the average that we want, which is the average of the lower and upper bounds, which is the expected average of this uniform distribution. Now you could also say plus the mean of data, that would give you the empirical mean of this sample data set. Okay, so I hope that makes sense. It's just a sequence of transformations. It's min-max scaling, Fisher-Z, so this is a nonlinear transform, and then another linear transform just to mean shift the data. Okay, so then you see this is the expected mean and our empirical mean. They match perfectly. That's beautiful. Here is where I create the histograms. And yeah, looks good. One of the concepts that I would like to stress with this exercise is that it's not often the case. Sometimes it's the case. Okay, sometimes it is the case that you only need to transform the data once, but often it is the case that you need to apply multiple transformations, so a sequence of data transformations in order to obtain the data characteristics that you want to get. And sometimes that is linear transformations, sometimes nonlinear, and also pretty often you will find that the best transformation protocol is a set of linear and nonlinear transformations. Welcome to exercise 5 of chapter 6. This exercise is all about Z-scoring, or as they say in the other side of the Atlantic, Z-scoring. Let's see. So there's two parts to this exercise. One is to implement Z-scoring or Z-scoring manually by translating equation 6.1 into code. And then you want to compare the results of your manual implementation of Z-scoring to the implementation that is provided by scipy.stats. So let me first go up to equation 6.1 just to remind you of the formula for Z-scoring. Here is that formula again. We looked at it in the previous video, or maybe it was 2 videos ago. Anyway, this should be pretty familiar. As you learn statistics, as you go through your life as a data scientist, you will see Z-scoring come up over and over again. Super simple. It's each data point minus the mean divided by the standard deviation. So implement that formula in code and then compare it to scipy.stats, or the Z-score utility in scipy.stats, and start by applying this on a NumPy array of integers 3 through 9. So then you want to use scipy.stats.z-score and your own implementation of the Z-scoring method, and then just print these out to confirm that they are the same. That is part 1 of this exercise. There's another part to this exercise, which I'll get to in a moment. First, I just want to quickly show you the code for the first part of this exercise. Here I create an array of numbers 3 through 9. Here is my manual implementation of the Z-scoring method. So it's the data minus the mean divided by the standard deviation. And you can see I'm using DDoF or DDoF, the denominator degrees of freedom parameter, to be set to 1. This gives us a sample standard deviation. Okay, and then here I'm using the Z-score function in the scipy.stats library. So you just input the data, and now you also need to provide the denominator degrees of freedom parameter, which from here inside this function gets passed onto the numpy.std function like this. Okay, so Not surprisingly, we print out these two vectors and they are identical to each other, which basically just shows that this function implements the same thing that this implements. But it turns out that stats.z-score has a couple of additional options that allows you to do the z-score transformation in more flexible ways if you have a matrix of data. And that leads me to the second part of this exercise. The second part of this exercise is about z-scoring when you have data that are stored in a matrix. Now, when you have data in a matrix, you basically have three options for how to transform the data or how to apply the transformation. You can apply it column-wise, so each column, independently of every other column, gets Z transformed. You can apply the Z transform to each row independently, or you can apply the transformation to the entire matrix. So instead of thinking about the matrix in terms of a set of columns or a set of rows, instead you would just compute the average of all the elements in the matrix, the standard deviation of all the elements in the matrix, and then z-score all the elements in the matrix together, not according to each individual column or row. Okay, so that is the idea of this next part of the exercise. So what you want to do is create a data matrix that you see here. It is the numbers 0 through 11, then squared, and then organized into a 3 by 3 matrix. So you can see this is 0 squared, 1 squared, 2 squared, 3 squared, 4 squared, and so on, up to 11 squared. So now we have this matrix, and the question is, do we want to z-transform the data in this matrix according to each column, or according to each row, or according to the entire matrix? So here I only specified to do it two ways, column-wise or matrix-wise. So here's the column-wise z-score transformation applied to this data matrix. And, we can do some fancy math in Python and sum or average, but I think you should be able to look at these numbers down the column and just already have the intuition that the sum over all the columns is going to be 0. So yeah, I think, without doing any exact calculations, just eyeballing, and it seems plausible that the sum along the columns is 0. On the other hand, the sum along the rows is obviously not going to be 0. I'm saying sum, but I also mean average, because if the sum is 0, then the average is also 0. This is just one way to confirm that the z-scoring worked correctly along the requested dimension. So here, the average across the rows is obviously not going to be 0. So these data are not z-transformed in the rows. Okay, and then here, when we look at the matrix-wise z-scoring, also obvious that the rows are not going to average to 0. It's also obvious that the columns are not going to average to 0. Look at this. Here, we have minus 1 point. So all of this, the first three rows in the first column here are close to minus 2. And this is nowhere near minus 2. So these are not going to average together to 0. Instead, the average across all elements of this matrix, all 12 elements in this matrix, that is 0. And the standard deviation across all 12 elements is 1. Okay, so this you implement. I suggest just to implement it in scipy.stats.z-score. If you would like to implement it using your own code, that's also fine. It's not super difficult to do that. But yeah, in this case, I only did it using the z-score function. So here is where I create our little data matrix. I have a range of integers from 0 to 11. I reshape it to a 4 by 3 matrix, and then I square all the individual elements. And here is the key part of this part of the exercise. Here's the key lines of code. So stats.z-score, input the data just like we did before, specify the denominator degrees of freedom to be 1, just like we did before. But now, because this data variable is a matrix, it's a multi-dimensional array, we can actually specify the dimension along which to average and compute the standard deviation. So to apply the Z transformation. Axis equals 0 would mean the columns. We could say axis equals 1. This would be the rows. And if we say axis equals none, then the mean and the standard deviation are computed based on all of the elements in the entire matrix. Okay, so then we print this out, and yeah, we get the same results that I showed in the slides. If you like, you can compute the average and the standard deviation along the columns. You'll see that those are respectively 0 and 1. And here you will see that the standard deviation and the mean along the columns is not going to be 1 and 0, respectively. But the mean and standard deviation across all the elements in the matrix will be 0 and 1, respectively. The goal of exercise 6 in chapter 6 is to use the Fisher-Z transformation to generate data, random data that have a particular skew. So you can see the histograms that I've created here. This data distribution has very little skew, almost 0. Of course, due to like just chance, just random sampling variability and noise, it's not going to be exactly 0, but that's fine. Very little skew. Here we have a data set, random numbers with a positive skew, random numbers with a negative skew. So I would like you to devise a way to use the Fisher-Z transform to create data distributions that look like this. So generate the distributions, generate the histograms, plot them, compute their skew, and so on. Now, you don't have to get your skew values to match exactly. That doesn't really matter. I don't care. It also doesn't matter what are the actual data values. You can see I've even removed the X-tick labels here, or the X-ticks, because I don't want you to worry about that. Basically, just worry about figuring out a way to generate data that have no skew, positive skew, and negative skew. So this one is a little bit tricky, but once you get the most important key insight, then from there it's relatively straightforward. So the key insight is that the Fisher-Z transform has relatively little impact on numerical values that are close to 0, and it warps the data a lot more the closer the numbers are to 1. So therefore, you can induce skew by just changing the range of the numbers that you use to generate the data. So in particular, we start with uniform distributed numbers between -1 and +1. And you can see I'm excluding exactly -1 and I'm excluding exactly +1 just because the Fisher-Z transform is not valid on those bounds. It's really exclusive bounds that we want to simulate. Okay, so then this is going to give us no skew because this is a symmetric uniform distribution. Here I have an asymmetric uniform distribution. So it goes up to +1, but it only goes down to -0.2. So that means that there's going to be a much stronger pull on the right compared to on the left. And then here I've done the opposite, and yeah, I just changed these values here just to get slightly different numbers of skew. Okay, so then we have the 3 data sets. Here I compute the skew values using stats.skew in the SciPy library. And yeah, then I just make the histograms with the titles according to those skews. So there you go. Now you know how to simulate data that have a particular value of skew. Now, if you want these numbers to have certain numerical ranges, well, you already know how to do that from earlier in this chapter. You can apply linear or nonlinear transformations to get these data into whatever is their current scale into whatever scale you need the data to be. Here we are with exercise 7 in chapter 6. This is going to be a really fun and interesting, insightful, enlightening exercise, but it is a little bit involved. It requires more time, might be the most time-consuming exercise in this chapter. It also refers back to an exercise in chapter 4, and the pages and the references here are ghosted because I'm writing this book in LaTeX and I'm only compiling one chapter at a time. These cross-chapter references don't stay. Anyway, let me quickly show you this. So this is in chapter 4 and exercise 8. So this is, again, chapter 4, exercise 8. Remember, the goal of this exercise was to create distributions with different properties and show that that affects the statistical moments. In this case, we were really focused on kurtosis. and the impact of these different distribution parameters on kurtosis. Okay, so if you haven't solved this exercise, I recommend doing that before you get to this exercise, exercise chapter 6, number 7. And that's because a lot of the code that you need for this exercise, actually you can copy and paste directly from the exercise 8 in chapter 4. Okay, I hope that makes sense, but it might be a little bit confusing, but I'm trying to make cross-chapter links here. So here's the idea. You want to generate random data from an exponential distribution, as you did for exercise 8 in chapter 4, but use a slightly different range of sigmas. So you're going to use sigmas from 0.2 to 1. This is from chapter 4. So here in chapter 6, exercise 7, use sigma in a range of 0.2 to 1. Otherwise, initially the code for the visualization and generating the distribution is very, very close to exercise 8 in chapter 4. Okay, so now what you want to do is for each data set, that is each value of sigma, you want to compute the standard deviation, the MAD, the mean absolute difference, and the scaled mean absolute difference, which is the denominator of the modified z-score in equation 6.6. Okay, I'll show you equation 6.6 in a moment. And then you want to generate a figure like this. So this figure looks quite similar to the figure for exercise 8 in chapter 4, slightly modified. Okay, what are we looking at here? Here we see the standard deviations of each of these distributions. These are distributions that are all based on the same normal distribution passed through an exponential, so a log normal distribution, with different values of sigma. You can see that when sigma is small, the distribution looks like a Gaussian. It looks a bit like a normal distribution. The larger sigma gets, the more non-normal it gets. And in particular, it gets really skewed to one side. So that changes the skew, it changes the kurtosis. But importantly, and relevant for this exercise here, it also changes the median, and therefore any metric that's based on the median. Okay, so here we have the median absolute difference, and we can call this like the raw or the unscaled median absolute difference. And here we have the scaled median absolute difference with the x's. So what you see is that neither one of these median absolute difference metrics is exactly following the standard deviation, which is fine. Given a non-normal distribution, you actually don't want these to be the same, right? You want them to be different. Obviously, the means and the medians are very different in these different distributions. So they should differ. But you do see that for relatively small values of sigma, when the distribution looks more normal, then the scaled MAD actually looks more like the standard deviation compared to the unscaled MAD or the raw MAD. So this is a useful property because it means that when a distribution is close to being normal, the MAD and the standard deviation will look pretty similar to each other. And as the distribution becomes less and less Gaussian-like or normal-like, then the standard deviation and the MAD will, of course, diverge more. So I hope that's clear. That's the goal of this exercise, basically, is to produce this figure. Now let me scroll up and show you equation 6.6. Okay, so here we have the equations. This is the the raw MAD or the unscaled median absolute difference. It's just the median of all the absolute values of the divergences between each data point and the data set median. So it's kind of like the standard deviation, but it's a non-parametric median-based alternative to the standard deviation. Okay, and then here we have the MAD. So, the scaled MAD. So basically you just multiply MAD by 1.4826. In the book, I talk about where this crazy number comes from, why it's 1.4826. That comes from basically just a guess of probability density estimate. And it's really just meant to be a scaling factor so that the MAD and the standard deviation are more similar to each other when the data distribution is roughly Gaussian. Okay, so quite a bit of explanation about this exercise, but like I said in the beginning of this video, it's a fairly involved exercise. but I think it is really informative. So I hope you enjoy working through this exercise. Now I will switch to Python and show you my code. As I mentioned, a lot of this code here for this exercise is copied from the code for exercise 8 in chapter 4. So this is slightly different because in chapter 4 is 1.2, here it's 1. Don't remember if there's a reason why I did that. I think it's just, it gets above 1, the scaling just gets too big. Okay, so generate a bunch of random numbers. Let's see. So here I generate the data as e to the x times s, where s is each value of sigma. Here I compute the standard deviation, and here I compute the median. Now, the median absolute difference. So you can see it's all of the data points minus the median of the data. And then you take the absolute value of those differences, and then you take the median of that absolute value of the differences from the median. Okay, now this is not the scaled median absolute difference. Scaling is just one factor. It's going to be a constant factor for all of these elements, all these different data sets, which are all these different values of sigma. So we don't actually need to do it here. I'm just going to scale directly in the plotting. Okay, so let me run that code. And here we get to the plotting. Here you can see I'm plotting sigma by m. So this is the standard deviation by m, the second column. So this is the median absolute differences. And here is the same thing as here. So it's still the median absolute differences. But now I am scaling by the probability density corresponding to 75% of the normal distribution. Again, if this seems really weird and incomprehensible, then you can check out the text. I discuss this in more detail in the body of the text. Okay, yeah, and then this is, I'm not going to go through this because this is really exactly the same as for chapter 4, but this basically just adds some nice features to the plot. Okay, so then, yeah, so here you see the plots again, and I don't have much else to say, but besides what I've already said. Basically, the idea of scaling the median absolute differences is that it looks more like the standard deviation. It's numerically closer to the standard deviation for data distributions that are approximately normal. Here is exercise 8 of chapter 6. I really hope that you are enjoying working through all these exercises. I tried to design these exercises not to be just kind of tedious, busy work, but instead to be sort of fun and require a little bit of creativity, a little bit of dedication, a little bit of focus. And yeah, I laugh when I said fun because I enjoy coding exercises about statistics and machine learning and data science. It's admittedly a pretty nerdy thing to enjoy, but that's just life. Okay, so here again, we are focusing on transformations of data to make them be more normally distributed. Not necessarily a perfect, pure Gaussian, but at least closer to a normal distribution than the original data distribution. Now, in this chapter, I've shown you linear transformations, nonlinear transformations, multi-part transformations, so where you apply a sequence of data transformations in succession. What we are going to do here is super duper simple. And basically what I'm saying is that the difference between two non-normally distributed data sets can actually be roughly normally distributed. Now, that is not trivially the case. That's only true for two distributions that are similarly scaled and that their distributions should be roughly comparable. So don't think that it is always the case that any two random distributions that are non-normal can be subtracted and the result will be normal. But it is the case here in this exercise. So create two data sets that have n equals 300 in each data set, and they should be somehow non-normally distributed. I did this using a power law distribution. Okay, so what you see here is the two distributions, two histograms of our two samples. Now you can see two important features. One is that they are very strongly non-normally distributed. It's definitely a non-Gaussian distribution. And two, both of these distributions, both of these samples are in the same scale, more or less. I mean, this one looks like it's a little bit larger, but basically in the same scale, and they have the same distribution shape. So then the idea is we imagine that these two samples are paired. They are linked together somehow. So we would perform maybe a paired samples t-test or maybe a correlation analysis. Somehow the data in these two samples are paired. So therefore it is valid to subtract the data points one by one for each of the two samples. And then we can plot the histogram, not of the individual data values, but their differences. So this is the difference between each of these data points, and then we take the histogram. Now you can see, as I mentioned in the beginning of this video, this is not a perfect Gaussian, and no one will ever claim that it is, but it is certainly a lot closer to a normal distribution than than either of these histograms. So you can see it has one peak and it has tails on either side, which are roughly symmetric, not exactly symmetric, but that's fine. Okay, so now I will switch to Python and show you my code solution. Well, this exercise is not super duper difficult to implement. I generated the two data sets using normally distributed numbers and then squaring them. Here I compute their difference, literally sample 1 minus sample 2. Again, this is valid if these data sets, I mean, of course, here these are just random numbers that I've generated, but you can imagine these are two paired samples in your real experimental data. So we can just subtract them, we compute their difference. Here I take the histogram of each sample individually, and here is the histogram of the difference between those two samples. And lo and behold, we see that the difference between these two samples is closer to a normal distribution than that of either of the samples alone.